Okay, in this video I'm going to talk about Chapter 5 of the Cisco ONS system, and Chapter 5 talks about optical amplifiers. Okay, so the first page I printed out happens to be probably the second page of the chapter. In any case, this page gives us a nice summary of the amplifiers covered in this chapter. There's a whole bunch of different optical amplifier modules. You can see some of them have the letter C in them, some have the letter L for the C band and the L band. And let's see, there's even more than that in this chapter. Let's see. Okay, yeah, our compatibility chart gives us a good list of all the amplifiers in this one. And as usual, it also gives us a nice window into the order of the release of these different products, because the newer products down at the bottom here are not compatible with the oldest versions of the software. So version 6 of the software only works with these top 3 amplifiers. Okay, so you can see as we go to later and later versions of the hardware or the software up to Rev 9.3, which is, I believe, the 2011 release, because this document was updated in 2011, and I think they added all these columns here. And in the 2011 release of the documentation, they must have also added these 4 amplifiers down here, because the last 4 are the only ones compatible with the new release of the software. Okay, so you can see now we have the name optical preamplifier, optical booster amplifier, maybe BST, boost E, boost L. Okay, optical amplifier L, optical amplifier 17C, maybe it's made to use for 17 channels in the C. Optical amplifier in the C. Here is a ROM. I believe that's a Raman amplifier. I believe the ones that are labeled Raman are definitely Raman amplifiers. And finally at the bottom, the Opt EDFA. I guess these are the optimized EDFAs. So what we'll do is we'll go through and look at some of the features of these things and some of their block diagrams. The very first one, the earliest one of the release, is called the Opt Pre. And here's its block diagram. We have the optical module with 1, 2, 3, 4, 5 optical ports. You can tell these are optical ports because of these little spools of fiber shown here. This is sort of the universal diagram for a optical fiber. Okay, and this optical module is controlled by a processor. We've got power supplies and an FPGA here for management. But probably the most interesting is the actual optical module itself. We had 5 ports. Well, here we have our comms receive and our comms transmit. Okay, and we have 2 optical amplifiers inside here. And this is very common configuration, where what we do is we have 1 amplifier, and then we go out to what's called DC transmit and DC receive. Well, DC stands for dispersion compensation, and this is a dispersion compensation unit, the DCU. And so the dispersion compensation fiber and the dispersion compensation, whatever unit you use here, generally going to be some DC fiber though, has high loss. Okay, and so what you do is you boost the power before you get into it, and by the time you come out of it, the power is low again, and then you amplify it again. Okay, so this first amplifier sort of compensates for the loss of the DC dispersion compensation unit. And there's a VOA here to make sure that a variable optical attenuator makes sure that you're sending the right power into the dispersion compensation unit. And then you have your transmit after that amplifier, and then you also have probably a 1% tap coming off of there for monitoring purposes. Okay, so that's the simplest type of optical amplifier design, and it's really 2 optical amplifiers with the dispersion compensation ports in it. Okay, Here is another one of them. I just picked a few of them to show the block diagrams. This is the op-amp L block diagram, so I think this is an EDFA which has been optimized for the L band. It's possible. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 optical ports with the same sort of electronic control. 10 optical ports. Well, we have the same 2 amplifiers with DC transmit and receive. So we have a dispersion compensation unit here. It's called an external mid-stage loss. So you're allowed to put something very lossy in between these 2 amplifiers here. It's for dispersion compensation though. And why do we have so many optical channels? Well, we have the same monitor channel coming out and the same line coming out, but now we have an additional optical element which multiplexes in that optical service channel. So these amplifiers are EDFAs and they're not meant to amplify the optical service channel at 1510 nanometers. Okay? And so you have to have a separate element to put that service channel into the signal just before you send it out on the line. Similarly, on the receive section, so that was the transmit section. On the receive section, as soon as you receive that signal, you're going to drop the optical service channel. So here we have OSC drop. And again, this is an optical element which causes the 1510 to go off on this output and causes all other wavelengths to go off on this other output. And then again, here we have a tap, probably a 1% tap for our monitor, and then our transmission. So on the receive section, all we're doing is stripping off the optical service channel. On the transmit section, we are amplifying, putting in dispersion compensation, and then amplifying again, then adding the optical service channel and sending it out. Okay, so this is one that has not only the mid-stage dispersion compensation capabilities, but also service channel add and drop capabilities. And that's why it has 10 ports. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Here is the Amp 17C block diagram. So this is yet a different one. Oops, sorry. And this one has 8 optical ports with electronic control. Let's see what the block diagram of this one looks like. This is another variation. Let's see. In this one, we only have 1 optical amplifier, so we do not have any mid-stage loss elements. We can't put dispersion compensation in line with this amplifier. But you'll see that this amplifier has some connection between the receive side and the transmit side. Okay? And before we look at that connection, let's just look at all the things that are going on here. On the receive side from the line, the first thing we do is we drop the optical service channel, and we then have the optical service channel dropped, and then we also monitor the optical service channel with a photodiode. So this little thing here it looks like a multiplexer, but I think it's just a tap, a 1% tap. So we get a monitor on the optical service channel here. So the first thing we do is drop the optical service channel, and then what we do is we also have a way of dropping part of the actual transmission, and we can pull that out for a monitor, but we also use some of that in a photodiode for feedback. Okay, so finally, most of the signal after we drop the service channel is going to go straight on through here. A little bit of it comes off so that we can monitor it, and some of it is also used for the feedback. On the other side, we have the COM RX, the COM receive. We have a tap, which allows us to monitor that signal. We have our EDFA finally. We tap off of that for a monitor to monitor the transmission, photodiode to monitor that, and finally we have the capability of adding the optical service channel with monitoring on another photodiode here. And APR, I believe this stands for automatic power automatic power what? I looked it up earlier. Automatic power reduction is what it is. So what this allows you to do is have some feedback which allows you to control the amplifier gain based on the incoming power. Okay. So this is useful. It allows you to have sort of an automated behavior of this amplifier, and that may be useful, for example, when you have DWDM systems with various numbers of channels turned up. If you buy a 32 or a 40 channel DWDM system, you may not turn on all the wavelengths at once. You leave some of those, you use the wavelengths you need when you first buy it for the customers you have, and then you have the capability of adding new customers, and the gain on the amplifier will change depending on the number of wavelengths that are present and actually turned on in your system. And so this feedback is very useful for that. Okay. Let's see, a couple more optical amplifier block diagrams. Optical amp C, 10 ports. You know what? It turns out this one's just like that optical amp L that we already looked at. Opt amp L and opt amp C. Same thing. OSC add and drop, mid-stage access. Okay, so we've seen that one before. But this one's in the C band rather than the L band. Okay. Finally, we have those last two amps called the Opt EDFA 17 and the Opt EDFA 24. I guess this is the optimized designs. And look at this. The 17 and the 24 cards are C-band, DWDM EDFA amplifiers or preamplifiers, 20 dBm output power. They do not contain mid-stage access loss for dispersion compensation, but they have noise figure optimized version of the EDFA amplifier to cope with new modulation formats like PM, DQ, PSK, which do not need dispersion compensation. Wow. Okay, so there are some very new, added in 2011, remember. If you look back here, these cards were added in, oh no, I guess not. They were added back at Rev 8.5. In any case, this is the newest thing, and they're dealing with some modulation formats that don't require dispersion compensation. They support 96 DWDM channels with 50 gigahertz channel spacing in the C band. That is from 1528 to 1566. And they have lots of features with gain flattening filters. Remember, I showed you the gain curve of these things, and it's nice to be able to have a flat gain. So these are actually very simple. They do contain service channel add and drop, but they're just a single optical amplifier, and they call it a true variable gain EDFA. And so this is the fancy new component here. Okay, that's enough on optical amplifiers. Thank you.